Okay, good afternoon, everyone. It's 2 o'clock, but I know that there is another seminar going on right before this one from Digital Forest Initiative. So I'm gonna give a few more minutes until we start our geomatics seminar series today. So let's wait a few more minutes so that we're gonna have more people in the room. Okay, it sounds like we're not going to have any more students coming in or new faculty. So let's get started. Welcome to Geomatics Seminar Series. Today we have a speaker who is a Purdue alum as well, Dr. Zhang. And quick introduction of Dr. Zhang. She received her BS degree in Aeronautics Engineering and Master degree in Instrumentation Science and Optoelectronics Engineering from Beihang University in Beijing, China. And since then, she joined Purdue and she received her PhD degree in 2017 from Geomatics, Civil Engineering under the supervision of Dr. Crawford. And she is currently an assistant professor in Biological System Engineering and Electrical and Computer Engineering at the University of Wisconsin-Madison. And her research interests include UAV-based imaging platform development for precision agriculture, high-throughput image-based plant phenotyping, multi-source motion sensing data fusion, machine learning, and its related application to remote sensing data. So with that, Dr. Zhang is going to give us a presentation about her current research program. That is also, I'm part of, participating as a part of the, the investigator. So I'm really excited to hear more recent update, from my research group. With that, Dr. Zhang, floor is yours.
Okay, thank you, Jinha, for the introduction. I'm really excited and honored being invited to going back home virtually. So I'm happy to meet everyone here today, and today I'm going to present part of my research, like alpha yield prediction using UAV-based hyperspectral imagery and ensemble learning. So first of all, I would like to briefly introduce my research focus. My research mainly like interdisciplinary research. So one part of my research focuses on using these remote sensing tools, for example, like gathering the data using satellite imaging, using drone imaging, or using robotic platforms. On the other hand, I focus more like developing these computational models or machine learning algorithms to extract informative features out of this multi-source data. At the end, we want to use these tools to support agricultural activities. These applications can be categorized into two parts. One is like this to support crop breeding. We can develop high throughput phenotyping tools to estimate the plant trees. Another part is like more like a precision agriculture projects, which we want to like minimize the farm inputs like nitrogen, labor or water resources input while maximize the production like crop yield. Today, this study focuses more on the second category, like the precision agriculture applications. So today I'm going to talk about hyperspectral data. I'm sure you took like remote sensing classes, know it already, but for those individuals who are not quite familiar with hyperspectral, I want to give a brief intro. So everyone knows about this traditional RGB camera. For this RGB, we can get clear, nice pictures, but it only gives us 3 bands information, like you can see right here, 3 color bands, blue, green, red, and that's why it's called RGB. So it does give you the spatial information, but it doesn't give you much about color information in the spectral domain, since it has only 3 color bands. Well, especially agriculture, only using the RGB, the 3 color bands information is not enough. Then we have developed this kind of multispectral sensors by incorporating more color bands, which located in the near infrared region, like here, these gray bands recorded in near infrared, which cannot be seen by our human eyes, but fortunately can be detected by sensor. And this near infrared information is particularly sensitive to the chlorophyll content, so we can use those to detect whether the plant is healthy or under stressed. So now compared to RGB, it's more bands are added, but still, it's still like quite a few, usually less than 10. So for some particular applications which require even more color or spectral information, the multispectral is not sufficient. So then the hyperspectral data could help in this case. Compared to the multispectral data, hyperspectral data can give you more, even more, not about 10, maybe hundreds of spectral bands. So instead of seeing this individual spectral values across the wavelengths, we can see a continuous spectrum for each particular pixel. Okay, because each spectral band is so narrow, so we can see this continuous spectrum. This is like the fingerprint for our human beings. So each object has a unique spectrum, then we can use this to really distinguish different objects. Hyperspectral imagery has been widely used in different applications like precision agriculture, environmental monitoring, food quality analysis, and etc. So today our focus crop is alfalfa. So what's alfalfa? You see this picture? It's a kind of grass. It's pretty small, very short, and it's a valuable forage crop with high yield and nutritional value. It's mainly used for like a feedstock for livestock, like dairy cows. Wisconsin, it has a big dairy industry, so alfalfa is a very important crop in Wisconsin. So unlike other traditional crops, corn, soybean, which is harvested only one time, usually in late August or early September per year, alfalfa is a perennial crop. It grows throughout multiple years, usually 3 to 5 years. And it follows a monthly harvesting schedule. Say in the whole summer, we need to harvest it multiple times every month, starting from late May, early June, early July, early August, until early September. In harvesting alfalfa, different machinery traffic equipment needs to be applied. So this picture can give you a better understanding how everything works. First of all, we need to have a mower to just mow the grass, alfalfa, and cut it. And then we don't do anything, just to leave this grass on the ground to let it dry. After a few days, we use another machine to just rake it, just flip it so it can be better dried. Once it's fully dried, then we will use another big machine to just bale it. So you will see a lot of bales just on this dairy farms. At the end, once they are all baled, we will use another machine then to transport them to either for use them as a feedstock or just transport to the market to sell them. So here are multiple machinery traffic need to be applied throughout the entire alfalfa harvesting process. And you can imagine, because these machines are very big and heavy, they will cause a significant impact on the soil as well as on the crop itself. When we just apply this, right, they will just probably damage the crop and also the soil. So this wheel traffic from these machines has impact on soil health and crop production potential. Then given this background, people are interested in knowing how those machinery traffic would actually affect the crop yield or alfalfa yield, right? Then intuitively, we can just go to the field, do some destructive sampling and measure the yield and the quality of the alfalfa. But this way is tedious, time consuming, and not efficient. We think nowadays, since UAV and this sensing technologies become more and more popular, we think whether we can just fly over the drone and with hyperspectral data to fly over the alfalfa fields, right? And see how the traffic really affect the yield. We try to develop a model to estimate the yield and the quality under different traffic treatments. So we exactly know how the traffic would affect the yield and quality instead of doing this labor-based destructive sampling. So here is the tool we applied in this research. This is a DJI M600 drone. And in this study, we mount a hyperspectral camera on a gimbal just to stabilize the camera. And on top of the camera, there is a small a GNSS INS navigation system. This is used to provide the location and the orientation of the camera in near real time. So we can record the camera movement just throughout the flight. So we can then further use this information to georeference the data. So for this study, we have 3 objectives. First of all, we want to investigate the potential of using the hyperspectral images for alfalfa yield prediction. Although we see lots of studies using the UAV hyperspectral data for like corn, soybean, or other kind of crops, but very limited research focuses on forage crop, which is used like fish for livestock, not for human. And also almost no study focus on alfalfa, which actually is a very important forage crop. Then another objective is more from the machine learning point of view. We develop an ensemble learning model to improve the prediction performance compared to the single learning models. At the end, we want to evaluate our proposed model, the adaptability, and the different machinery compaction treatments. So here is our study area. We have this in one of our agricultural research stations. So we randomly designed with 7 different levels of machinery traffic treatments and 3 replications for each treatment. So each black box you see here representing 1 plot. Again, since this is a precision agriculture application, the plot is relatively larger. So we have a 3 meter by 3 meter plot, each black box. Here is a list of our machinery traffic treatments applied to our alfalfa plots. This study started in 2019. So T1 to T7 representing the 7 different treatments. So T7 is the control group, which means we didn't apply any traffic treatment. So 0 passes were applied. No machine effect applied, traffic applied, okay? And then T1 until T6, different numbers of passes were applied, and they were used to simulate different operation. As you see in the earlier picture, for example, we use 1 pass, and then we just can only simulate the mower step. And then we use more passes, we can simulate not only the mower, but merger, forage, harvester, right? Because it involves multiple steps for the whole harvest. Then just more passes means the more traffic treatment applied. Okay, a little bit more details about our data acquisition and pre-processing. So this is from Hello, and this is the characteristics of our hyperspectral data. It has more than 270 spectral bands ranging from the visible to near infrared from 400 to 1000 nanometer. And then we conducted 2 flights. actually more than 2, but only 2 were very successful in the 2019 summer season. 1 in late July, 1 in middle August. Each flight, we consider about the timing when we conduct the flights. Each flight were kind of 2 weeks before the harvest. So we try to use this data to develop models so that we can predict yield when the field were harvested. And then our flying height was 40 meters above ground. Our flying speed was 5 meters per second, and resulting in a GSD resolution about 2.5 centimeter. So the resolution, spatial resolution is pretty good for us. And here is how we set up the flight path, just some basic knowledge in case you are not quite familiar with UAV operation. So this is just the commercial software. We need to set up this flight path. When you set up the flight path, you need to consider how many passes you want to cover your area by considering your flight height, your spatial resolution, also the flight time. I want to point this out because this directly relates to how much battery you will use. Think about it, because UAV has a strong battery limitation. For example, this drone can only fly about 25 minutes. We don't want to exceed that because we don't really want to change batteries within the flight. So by considering all these factors, this software will help you automatically generate this flight path. And then next step, we need to select the flight polygon because we don't want to record data, store data when we are not within the area that's interested to us. So we draw a polygon and then upload this information into the camera. So the camera is only triggered when it's entered the polygon. This is how it looks like in the field. We use this internet cable to connect our laptop with the imaging system. Then once everything is set up, we can unplug it and just let it take off. Here is how we deployed our spectral targets, because we need to do radiometric correction for the hyperspectral data we acquired, which includes 2 major steps. One is we need to convert a digital number, which is the raw data we directly get from the camera, to radiance. This can be done by using the vendor supplied software. But the second step is to convert the radiance to reflectance. That's where we will need to use these calibration panels. So you can see these are actually 3 different colors with different reflectivity. So the brighter one is like 56%, and then the darker one is 11%. Then we apply them to convert the radiance to reflectance. Another major step, in addition to radiometric correction, we need to do geometric correction. We need to also rectify the data because we fly over multiple passes. We want to stitch them together. In this case, we need to use this GNSS, the small unit that's mounted on the camera, to geo-rectify all these passes and then stitch them together. This step is also done through the Hello software. And then the next step, you see, we need to do lots of pre-processing before real data analysis. Because we need to extract the plot level, because each plot is under a different treatment. We want to only extract the plot level data. So we need to draw these plot boundaries given shape files. We can do this in ArcMap. And within each plot, we also need to remove some shadows, noise, these black holes, right? How can we do it? Maybe in this case, you can use different strategies, but in this case, we use like an NDVI setup threshold. Say if it's higher than value, say if it's lower than 0.6, we consider non-vegetation. So in that way, we can extract only the vegetation pixels. Okay, after all this data cleaning, we got our organized clean data. Then first of all, we want to visualize our data. What's the hyperspectral, or what's the alfalfa reflectance look like under different treatments, whether there's enough variability to allow us to develop a meaningful or reliable machine learning model. Fortunately, we do see some variability across different treatments. For example, here, T1 and T7. T7 is the control group, which has 0 pass applied, while T1 is the group. It is the treatment has only single pass applied. Since we don't have much difference, 0 versus 1, so you can see these two hyperspectral data are just kind of overlapping with each other, right? The shaded area means the variance across all the pixels. And then when we look at the T6 versus T7, we can clearly see a difference in the near infrared region, which is from 700 to 1000 nanometer. We see the blue line is higher, has higher value than the orange line, which means the control group has higher reflectance value than T6, which has about 5 passes applied. So in this case, the plant is kind of damaged or under stressed because of this traffic applied. So we see a decrease in the reflectance values. Okay, because once it's under stress, the chlorophyll content would decrease, and then accordingly, the near infrared reflectance value would decrease. And if you look more carefully at this red range, which is about 700 nanometer, we also see clearly a small, not a big, very small increase in the orange versus the blue. Because once the plant is under stress, we do see a small increase in the red region. And that's exactly how, by knowing this pattern, that's exactly how the NDVI is defined, right? In NDVI, we use NIR minus red divided by NIR plus red. So that's the difference between the healthy and versus stress plants. So we don't really see a big difference, but we still see some patterns going on here, which means, okay, our hyperspectral data really can detect the effect of the different traffic treatments. So based on this foundation, we are certain that we are able to develop a model to estimate the yield across different treatments. Then we consider, okay, we have this more than 200 spectral bands data. What shall we do next? We actually explore different ways. We can just throw in all these 207, whatever this number of bands into the model, and then get some results. Also, we think about whether we can just use some vegetation indices and maybe compare these two ways, right? Whether using old original data or using vegetation indices, which way is better? So to investigate VIs, we just did a comprehensive literature review. We found out all the 80 published hyperspectral indices, as we listed here. This is not a comprehensive list, but we kept this in the published paper. So we gathered these 80 vegetation indices. And each index actually is derived from 2 or more spectral bands. We found out that, even though I didn't show it really here in the results, but we found out that using this method is a little bit better than using all the spectral bands. So I just continue with using these VIs. Then we think whether we can do some feature reduction to the 80 vegetation indices rather than using all of them. We explore some simple feature selection method. Finally, we end up with this one, which is called recursive feature selection approach. I won't go much details about it. It's an existing method. It's not a method we develop. It's just an existing method. We apply it. And however, actually, this is based on some kind of prediction results based on so we can imagine if we change our training data, then the prediction would be different. So instead of just running one experiment, we run by using different random seed, see how the training and testing separated. We run 250 number of experiments, then we get somehow this kind of histogram. We found out for some indices just consistently perform more important than some others, like this one in this category, the dark red. Then we train and we further think what kind of model, we have the features, then what kind of machine learning model we should use. In most cases, people tend to use a single machine learning model. It can be a neural network, can be random forest, decision tree, all these different single models, and train and apply the models. Or in another way, we can think by using some ensemble learning idea, we can combine the multiple prediction results, right? Through the ensemble learning, actually, it can help reduce the variance of your errors, so it can help improve the overall accurate model performance. In this case, instead of using a single model, we develop an ensemble model. So two things need to be considered when you construct any ensemble learning model. One is the sufficiency, which means each individual model should be accurate. Another is diversity. Somehow this diversity is more critical than the sufficiency because you don't want to have redundant information in your ensemble. You want to make sure all the base model you used in your study are somehow really different from each other. So by investigating the existing models, we finally decided to use these three. We didn't really choose a neural network because we have very limited training data. So we just use those traditional and simple machine learning model to form those use as individual models. And then we evaluated these three individual model performance by using different number of features. In total, we have 80, right? But we use those feature selection methods, which can help us really rank the importance of this 80. At each time, we just add one feature into the model, and then we found out that until 25, somewhere here, the accuracy for all the three individual models kind of got stabilized. They do not change much. So we think by adding more features into the model will not improve our performance. So we end up with using the top 25 features for model development. And then here is a scatter plot results for all the three individual models, like random forest, support vector regression, k-nearest neighbor, and the ensemble model. The last one is our ensemble model. So by looking at the R-square, RMIC, and MAE, we found out that the ensemble model achieved the best accuracy model performance. Also, interestingly, we observed that there are two clusters of data, and one in orange, one in green. So which means, okay, this green cluster yield, we are estimating yield here, is higher than this orange cluster. Remember, in this study, we use two harvest data. So these two clusters actually just representing the alfalfa yield data obtained from those two harvests, one in late July, one in late August. So we can see that actually the alfalfa yield changes through the harvest cutting. And then we applied back. Our third objective is to see how the model performed under different treatments. So we applied the individual model work as well as the ensemble model back to each individual treatments. We still found out that our model, the ensemble, the last row here, we consistently has the stable R-square accuracies. For some other individual model, we do see some good performance maybe in some of the treatments, but not good in others. That's the work we have done. Then we think because the alfalfa producers not only care about yield, they care more about these alfalfa nutritive values. For example, like the crude protein, the protein content. the detergent fiber, neutral detergent fiber, all this directly affects the forage digestibility. Actually, this NDF directly relates to the market price. If you reach a certain value, your alfalfa can be sold at a much higher price than if you don't reach that value. So this is actually more important than yield for the producers. So they need to determine this for the producers. How do they do it? They can destructive sampling this alfalfa data and then send the data into some forage lab. So the forage lab can do two things for them. One, they call this wet chemistry method. They just use some chemical analysis, just, it takes multiple days running some chemical experiments, then determine all these values. This is very time-consuming, expensive, and also it's not healthy, right? Because doing chemical analysis somehow can be harmful for human health. Or the other way, they use, this is more like a direct way, so we can say that that's the most accurate one. Or the other way they do is like an indirect way. They still use some like sensor technology. In this case, they use this near infrared reflectance spectroscopy. Actually, it's still the hyperspectral data, but it's not like, it has only one hyperspectral dimension. It doesn't give you the spatial, the imaging information. Also, it's benchtop. So you still have to go to the field, do the destructive sampling, and then collect your samples, and then dry your samples, and then grind your samples into small particles, and then put them into this system, sensor. Then, because they have the equations well calibrated, then they can apply the equations directly, and based on the results, give you all those nutritive values. So this way is also very expensive. Typically, if we analyze one sample, you need to pay about $20. Then we think, because this is just hyperspectral data, then we think why we don't just fly over the field, right? And then develop a model to estimate it. Because they use the similar concepts to just how to determine the nutritive values. So we just try it, and then we collect the data. In this case, the ground truth is not yield, it's this multiple nutritive traits. But interestingly, we have more nutritive traits, right? Through CP, ADF, NDF. But also they kind of related to each other. These are not independent with each other. So we think whether we can develop kind of multitask learning model by predicting them all together in one model, which can help us save some work. Instead of developing 3 individual models, we just develop one model. Also, more importantly, we can investigate the underlying cross-relatedness about this nutritive traits. So this is the neural network deep learning model we developed. First of all, we have our input layer, which is the time series hyperspectral data we collected. We use some common tools like long short-term memory, LSTM, which can really help you better handle the time series features. Then we map this into a common feature space. And starting from there, we just developed 3 individual branches. Each individual neural network would have a different kind of architecture. And we call this like task specific component, right? Because until here, everything is common. And then we further separate them into 3 tasks, with each task dedicating to each individual nutritive trait. Of course, you can add more. There's no constraints of how many tasks you can add. You can also add in the biomass or the yield, so you can predict all of them together. I didn't really show the results here, but actually we got this work done already. And we found out that this multitask learning model also performs better than using individual models. It's better than using traditional individual model like random forest support vector regression. It's also better than using individual deep learning model without this task-specific component. So the efficacy of the model is greatly demonstrated. Some conclusion of the work. In the yield, we first of all investigate some feature selection method. We found out that some multi-band indices ranked importantly than the two-band indices. This mainly because maybe the multi-band indices has more spectral information. Another important index we found out is called this PRI, photochemical reflectance index. It indicating the photosynthetic efficiency, and it ranked importantly. Regarding the ensemble model, we found that it can achieve the better performance than the single model. And we also realized that there are two things needs to be considered in constructing the ensemble model. One is the sufficiency, means that each model needs to be accurate enough. Another is the diversity. They want to be as different as possible. Regarding the future work, we already developed a multitask model to estimate the nutritive quality traits. We can further incorporate the environmental variables like the data we got from weather station, also incorporate some soil property variables to see whether we can further improve the model performance. That's all of my presentation, and I will take any questions you have. Thank you for your attention.
Thank you very much, Dr. Zhang. And I'll open the stage for question to the audience. So if you have any question, you can unmute yourself and ask question directly, or if you prefer, you can just type in your question in the chat window as well.
Excuse me.
Go ahead,
Did
Lina.
you hear me?
Yeah.
Yeah, sorry. I have a question. Actually, it's just for clarification. You had two data sets for different dates, right? For two different dates. And by the equipment, I actually didn't get it very well. You mean that different types of harvesting alfalfa, or it's like, because we have two fields, or it's been harvested in different ways?
These are two fields, but they located very graphically next to each other, pretty close.
Oh.
When we do the data analysis, because each field contains very little samples, which is not sufficient to any machine learning model. So we just combine them. We apply the same treatments to each field. So we don't really treat them like two fields. We just treat them like one field.
Okay, yeah, thank you.
Any other question from the audience? Don't be shy. We are not going to bite you. So since there's no question from the student, probably I will ask your question, one question, to see if this can actually help student ask more questions. So when you are showing those different spectral responses for different treatment,
okay.
It seems that we can see those difference, but those regions where we start to see those differences, those, for example, near-infrared region, difference is pretty much consistent. So what kind of advantage do you see for this kind of application for having hyperspectral data set over either multispectral or RGB? Do you see any specific advantage of having hyperspectral data for? I think there's two results that you are presenting here. One is yield, and the other one was quality. And
right.
to me, it looks like quality will benefit more by having hyperspectral than the yield. But to me, yield prediction, for example, multispectral data set might be good enough to predict the yield differences for different treatment as well. So do you have any thought on that?
That's a very good question. We didn't really investigate the difference between multispectral versus hyperspectral in Alfalfa, but we just got another manuscript drafted. That manuscript is to investigate the difference between multispectral versus hyperspectral for potato yield estimation. We found out that the accuracy, even though we think maybe not big deal, but we still see a huge difference between the multispectral versus hyperspectral. But the thing is, we didn't really compare the real multispectral sensor versus the hyperspectral sensor, because we think even from the different vendors, there might be different. What we did actually, we used the hyperspectral data, we collect hyperspectral data. Then we average over by using some Gaussian kernels to simulate the multispectral data. So we make sure all the data are coming from the same time, same sensor, but just with different number of bands, and each band has a different bandwidth. So we see a big difference between this hyperspectral versus multispectral for potato yield estimation. So my hypothesis here is, even though we didn't really do the experiments, but I think we probably still see a difference for alpha. But that's a very good thought, and that's a very popular question in this community because of the price, right? All these issues.
Yeah, because hyperspectral is such a beast to have a the system in place and establishing data acquisition the workflow is costs a lot of money. First of all, hardware is expensive, but training those folks in the field to collect the data properly, that is actually a lot more money than actually buying on hardware. So
right. So yes. So others also ask me the similar type of question. So it's very well solved.
Any questions from the audience? If I start to call names, force you guys to ask questions. And I guess that this is another kind of item that actually Lina and I've been discussing recently as well. And your current approach is having one-time hyperspectral measurement to estimate yield for the next harvesting cycle, which is about 2 weeks before harvesting. You flew the area.
Yeah.
What is your thought on having multi-temporal data acquisition acquired or being fed into your model to predict yield? For example, what I mean by that is instead of having 2 weeks before the harvest, you're going to fly one. What if you just have one more flight, like say 2 weeks before harvesting, another flight a week before harvesting, having 2 hyperspectral and the measurement collected, and now you have additional information, multi-temporal, available for your model to predict what the yield is going to be. Do you think there's any benefit of having that multi-temporal aspect incorporated your the prediction model?
Yes, absolutely. We did use the time series data in the quality, even though I didn't really show that. But in the yield, this is my first year here, 2019. We failed lots of experiments. Those are the only 2 successful data we got. Then in the 2020, our second year, we further evaluated the model using time series data. For yield, yes, there's improvement. Also, we developed the quality model just by using the more time series data for the quality models. So yeah, I think another future work we can do is, it's what producers mainly care about is, okay, so you use this 2019 data, you develop model, whether your model can be successfully applied into future years without, again, go there to collect ground truth data, retrain your model, right? Like transfer learning, all this type of work. So that's what they have been keep asking me, whether how much generability of your model it is for future years or for different farms for different locations. That's what they really mostly concerned about.
Sure. Like yield is such a complicated process. It's not just about soil compaction. It can be weather. It can be nutrient. It can be the seed quality. It can be management practices. There are so many things that need to go into. So the development model for 1 year is good. You get a very good result, but it is always questionable to see if you apply this model, develop model to another location in different years where we have a different environment, different treatment. Of course, it's not going to work. So how to make this model, transferable to another location? I'm pretty sure this, and everybody knows that this is a huge research topic, especially here in the Muslim society, and how to not only from the Muslim society, but in general machine learning society, how to make your model transferable from one location to another. And there's huge research going on transfer learning, and active learning is also another part. How to update your model with least amount of labeled data set for in a new location and etc.
Yeah. Yes, these are some emerging next topics.
So you want to share a little bit of your experience about your hyperspectral system that I know that you had a lot of issues with your first version of hyperspectral system. Now you're flying, what is that, the Griffin system right now? And this, the one that you're showing is not the Griffin system, right?
No, this is the version 1.
Okay.
So this is directly from Headwall. I just put everything together, but I bought all the parts from them. Then I just upgraded this system to the Griffin system, which doesn't have this gimbal anymore. So they just installed this hyperspectral camera. Also, they changed this, right? They changed this to like APX 15 more accurate version. And then they just mount all this within a black box to just protect it. And then we add in another high resolution RGB, add in a better than 16 LiDAR. And then they also offer us the software they used. So we don't use Headwall software anymore. Everything seems operational now. But we did spend lots of time on either this version or the Griffin version when we just purchased from them. So yeah, even we just purchased from them, it didn't really work as expected, but they fixed some of the problems for us. Then right now seems okay.
Great. Any further question from the audience? This is the last chance for you to ask questions if you have any.
Also, maybe I want to post a job advertisement. If you are interested in looking for like a postdoc or PhD, just feel free to email me, send me your CV. And our group is always actively looking for talented people to join us do this exciting work. We have both postdoc and PhD openings in our lab.
So Zhou, you want to show that website where you posted your job description?
Do I have I can show you my website.
Yeah.
But I think I have posted. Yeah, this is our lab website. Our lab is Digital Agriculture, Wisconsin. And we have these opportunities. Maybe this is a little bit outdated, but yeah, still like, oh, I don't have a deadline. So anytime if you want, you can just email me. So we have this postdoc position, which we can work on this UAV, hyperspectral, machine learning, or even just satellite images. Or PhD positions, we will offer compatible salary and insurance RA support throughout your PhD. But PhD have some like language. If you are an international student, has some English proficiency requirements. But just let you know if you are interested.
Sure. We have a couple of master's degree students in the room, so they might be interested. And I know there are a couple of PhD students who is getting close to their final stage of their PhD degree. So.
Great. Yeah.
Again, thank you very much for your time, Dr. Zhang, for your great presentation. I really enjoyed it. I hope all the students enjoyed your presentation as well. And that this presentation is being recorded. So this will be posted to our one of the YouTube channel that my research group is hosting, because we don't have a Geomatics YouTube channel yet. And those will be available later. So thank you very much and have a nice rest of the day.
Thank you. Yeah.
Bye-bye.
Thank you, everyone. Bye.